Welcome, everyone. Am I that loud? It's my dream to have a mic in my hand, not yours, though. Okay. I'm Erica Bowers. Welcome, everyone. I'm the director of the Faculty Development Center. It's our pleasure to host the Outstanding Professor Lecture this year. I've had the pleasure of working with Dr. Behseta to get this prepared, and I can definitely tell he has a fabulous rapport, I'm sure, with everyone he works with. So it's been a real pleasure working with Dr. Behseta. To kick us off, I'm going to hand the microphone over to Dr. Stang, the Associate Vice President for Faculty Affairs and Support, and we're going to work on a longer title. We're just not there yet. Here you go.
So we often joke, I also don't mind having the mic, but I want to welcome you, those of you that are joining us via Zoom, as well as those of you that are here in the room. So good afternoon. My name is Kristen Stang, and my title is now the Associate Vice President of Faculty Affairs and Support, or Kristen. You can certainly just use that. But it is my great pleasure to introduce and welcome all of you to our Outstanding Professor Lecture for this year. Each year, our campus honors a faculty member who has been selected by their peers. That's the important part. By their peers, to be the outstanding professor. It is the highest award the faculty can bestow on one of their fellow colleagues. To be selected as outstanding professor, the nominee must have a record of superlative teaching, distinguished scholarship, evidence of service to the campus and to our larger community, and have earned national or international, or maybe both, recognition in research and publications. This outstanding faculty receives campus recognition, an honorarium, and delivers a lecture to the campus, which is what brings us here today. Today's event is sponsored by the President's Office, the Office of the Provost and Vice President of Academic Affairs, the Academic Senate, and the Faculty Development Center. So it is now my great honor to welcome our president, Fram Rose Burgee, who will now introduce and welcome you to this year's Outstanding Professor Lecture. Thank you, Fram.
You know I don't need a mic, especially, but I guess we'll use it just to for the folks that are on Zoom and to record. That's the right thing to do. First of all, I just heard a great statistic that I have to share. Because, you know, of the topic. This is the 7th outstanding professor from the math department. And that is the most outstanding professors from any department in this university. Yeah. So with that, good afternoon and welcome to the Outstanding Professors Lecture. You can see the title up there, Statistical Thinking and Big Data Exploration. As I read the title, I thought nothing describes our outstanding professor better and his work better than what he does. Big data and lots of exploration. Unbelievable. At Cal State Fullerton, we often talk about the transformative power of education, the transformative power of the Titan experience. We talk about how that sets us apart from other institutions. One of the things that contributes to that mightily is the passion of our faculty, the passion of our professors, and how much they not just care about their topic and care about their subject matter, care about their academic excellence, care about their research, which they do, but also that they care even more about the students with whom they're sharing that information. To state the obvious, it's the goal of most professors to ignite their students' curiosity and to ignite that same passion in their students for their subject matter as they have. And that is exactly why we are here today. And while that passion is often evident in the professor, it takes a really special talent to engage the students in a way that they actually fall in love with their subject matter. Going off script for just a second, I remember I've told this story before, but it's special for me, and I hope it can be special for the math department. When I came here, I was enamored by student athletes. I was a student athlete in college, and I thought, my goodness, what better thing can you do than come to university and do the thing you love? You get to play baseball or softball or soccer or whatever it might be. And then I met our music students. Not only did they get to come and do that work in that area, but they got to actually major in their passion. They got to major in music or voice or acting. And I thought, okay, that's got to be it. And then one night I was walking back through McCarthy Hall, and I was walking through the halls, and I heard noise, and it had to be at 9 o'clock at night. And I heard noise, and I said, who the heck is here at this time of night? And I opened a door into a room, and there's a big whiteboard, and there's equations all over the board. And I said, what are you doing? Do you have a final tomorrow? No. Are you studying because you think there's some big research piece that you're going to have to do? No. Well, I said, what are you doing? We love math. And it hit me. If you find your passion, that's it for the rest of your life. That is what's going to guide you and lead you and get you up every morning and excite you about life. That is exactly when I say it takes a special talent of a professor, of a faculty member, to ignite that in their students. And as rare as that talent is, we have one, what do they say, in the house today, right? With our 2021-22 Outstanding Professor, Dr. Behseta. He's accomplished this time and time again. This is evident in the many awards that he's received, the grants that he's received. But I have to tell you, it was laid out even more substantively and impactfully in the 100 pages that made up his nomination package. Superlative after superlatives. His peers described him as a role model to most junior faculty and to one of the most sought after members of the department for classroom observations, for help in the classroom. He's always willing to provide advice and is a great colleague, a great sounding board. He's always willing to go out of his way to help others if he can. Well, what better way is there to define the mission, the raison d'etre of teaching, of a professor? Growing up in Tehran, Iran, during the constancy and the cloud that he found himself in politically, he turned to academia. He turned to learning, studying at the National University of Tehran. And as I shared with the Senate when we made this award, during that time, Dr. Behseta, he was inspired to pick up a copy of a magazine called Chance. And we've talked about this, a statistics magazine from Carnegie Mellon, a statistics magazine. I mean, are you kidding me? Now, I have to stop right there because I just admit it. I love facts. I love figures. But if you told me there was a statistics magazine called Chance, the chances of me picking that up are pretty slim. But not Sam. He not only read that magazine from cover to cover, every article, but in that magazine, he discovered his future. He discovered his passion. He discovered where his life was going to go. As another point of privilege, I will tell you here that as a person of faith, I find little in this world is left to chance, in my opinion. Instead, most often, what we see as chance is really intention, just wrapped up in direction. That's all it is. Chance, if you give us something a chance, it's going to guide you to your calling, to where you want to go and what you want to do. I know that I am very thankful that that fateful chance led me here to this university to do what I love doing and the passion that I have for what I'm doing. And the story is absolutely no different for our outstanding professor. This chance reading of this magazine set him on a course to aspire and then one day attend Carnegie Mellon, where that magazine came for, and in so doing earn his PhD in statistics and to change his life. And in so doing, that chance led him to us, so that he didn't just change his own life, but he's ever since been changing the lives of so many others. And we could not be more blessed to have that chance encounter here. His dedication to transform chance into change, it's potent. It's really potent. He has a keen understanding of how students learn. He transforms every classroom opportunity into an opportunity, every lecture, every office hour, every classroom participation into an individualized learning experience for his students. He believes in the critical role that learning through participation can play in communicating ideas, in solving problems, and in mathematical discipline, right? As he followed the data in his interactive learning theory, he's proven to be a student-centered, success-based professor based on positive feedback from his undergraduate and graduate courses in statistics and applied mathematics. He's not just won numerous awards, folks. He's got more than $6 million in grants and accolades all over the place. He's received so many at Cal State Fullerton, but all across the state, the country, and the world. In fact, the very words of his students are actually maybe best in conveying this. One student wrote, "He has helped me gain confidence in my own ability to understand the difficult subject, which he has translated into my approaches in the courses that I've taken." From another student, "He is truly a great professor. I am very grateful for his willingness to teach." Along with his amazing A's in his SOQs, he's always known for giving his time to his students, to faculty, and to folks that he doesn't even know that well, that he just is willing to help all the time, to help his students bolster their careers. He's modernized the probability and statistics concentration here at Cal State Fullerton, and he's championing bringing that Master's of Science degree to Cal State Fullerton. During these times, his students have had real world research experiences that match what they will need when they go out into the field. He's mentored more than 40 students, with many of them going on to advanced degrees. And during the pandemic, what did they do? He mentored a group of students who created a statistical model for COVID-19 pandemic data by studying how the virus was spreading throughout the community. Talk about real world experience. You couldn't get better than that. So Dr. Laura Chowdhury, an associate professor in the Department of Mathematics and associate director of the Center for Computational and Applied Mathematics. Boy, you think you got a long title. She commented that his heart and soul are devoted to teaching both inside and outside the classroom. His research is nationally recognized. His service to the department, to the university, to his community is extensive. He is a colleague that truly wants success for everyone that he touches, and he helps them in every way that he can. So today, as we look back, we are thankful for the chance. We are thankful for that chance encounter he had with that magazine, the chance encounter that changed his life, and the direction that had brought him in to be a beacon toward his true calling as an outstanding educator, a learned facilitator, and a real champion of beating the odds, right? Of not worrying about chance. One quick fun note as an aside that so many people know, and that is our award winner here. He had an opportunity to go back and become an advisory editor for the very magazine that started all this. What are the chances of that? So talk about coming full circle. These many chances, I believe, were never really chances at all. They were just they're a clear example of what happens when you follow your passion, when you follow your mission, and you follow through. Titan family, please join me in congratulating and welcoming our 2021-22 Outstanding Professor, Dr. Sam Behseta. I think I'm going to learn a thing or two now. Thank you so much. Appreciate it. I think they want to take a picture, right? Yeah. Okay.
Oh, got it all.
Ah. Oh.
Yeah, fancy it up.
Either side of this.
Big smile, ready, 1, 2, 3. I'm gonna go try really quick. Now 1, 2, and perfect.
You're good. You're in it.
All right. Thank you so much. Appreciate it. Yeah, I use the this one. Yeah. Thanks.
Thank you. Can you hear me? I can hear me. Thank you. Yeah, I'm good. Thank you. Appreciate it. All right. Well, thank you very much, Mr. President, for that incredible introduction. I'm deeply honored and thankful and grateful to all my friends and colleagues who are here. My dean is here, Dr. Johnson, Dr. Stang, Dr. Bowers, all my colleagues with whom I collaborated throughout years. Thank you, everyone who's listening to this here or online, or will watch the show later when they record it. So I'm truly humble and thankful. It's hard to think about how you can express your appreciation for a recognition of this caliber. So it's very hard to say that. All I can tell is that as a statistician, I have collaborated with many friends and colleagues in my department and in the College of Natural Sciences and Mathematics, and also across the campus. I worked with people in School of Business, School of Public Health, School of Education, and I can attest to the fact, I have a lot of data to say with high probability that there are very many outstanding professors in this institution. And so I take this, recognition as a gesture towards what we do collectively in educating our students. And so I'm humbled by that. And also, when I was approached to give a talk about what I do, it's always easier to talk about technical things. It's almost always easier to talk about your research to your peers. It's non-trivial to tell the story in a non-technical way. So I figured the best way I can approach this is when, in the math department, every semester, a day or two or a week or two are devoted to advising students. When they come to me, they ask, why should we do statistics or data science? So I already have some answers prepared after many years of advising. So I figured that's the best way to start this conversation. It used to be hard to justify why statistics is useful, but nowadays it's an easy sell. Everybody's aware of the fact that we're surrounded by data. Data is increasing in volume, in forms, and quality. And so there is a real need for people who understand data, can analyze data, and can make sense out of it. And in fact, I would argue that there is a need for statistical literacy. That is, every conscientious citizen has to have some level of understanding numbers, especially in the day and age where people fabricate all sorts of things under the name of being covered with data. So it's a very important discipline, I would argue. And, so that's easy. Statistics is important. What is data science? I really don't know. There's no universal definition about data science. It sounds like what it should be. It's a science about data. It's probably where mathematics and statistics and computer science meet. Those skills are required. I can tell that much, that you can do good things with data science if you have that fundamental knowledge about these disciplines or approaches associated with them. And what is statistical thinking? When I advise students, and if by that time I still have their ears, I say a few words about statistical thinking carefully about what contributes to uncertainty in the data that they have collected or they are going to analyze. So I've throughout years have developed some sort of a framework for what statistical thinking is supposed to be. To me, the first question that anyone should ask when they are encountered with data, with numbers, is that what is the source of that data? Where does it come from? How reliable that data set is with which you're trying to build inferences. And when I get to that point, I tell a story about the origin of two of the most celebrated stories or terms in all of statistical discipline. Anyone who's taken some course in stats, whether in high school or in college, has heard the terms correlation and regression. Those terms are really devised by these two pioneering mathematicians. The gentleman with the hat is Francis Galton. The one next to him is Carl Pearson. Pearson is a very important figure in the history of statistics because around 1910, he starts the first statistics department in the world, University College London. He publishes the first journal in statistics in 1900. The journal is titled Biometrica. And so, Galton is fascinated by the idea of correlation. What Galton does is that he runs an ad in a newspaper in London, and he invites people to go to his offices so he can measure their heights and their kids' heights. He's after correlation, association between the height of parents and children. He wants to predict children's heights based on their parents' heights. That's actually his notebook. You can see that he meticulously have written all the measurements in his notebook. And, we take this data set to our classroom. This is Galton's data. By the way, all the figures that I'm showing in this talk are generated by our students. So I'm very proud of that. So, you don't have to have much mathematical training to appreciate the fact that every dot in there on the x-axis is the parent's height, on the y-axis is the child's height. So every dot represents a parent and a child height. An overall pattern of this data set is positive, meaning that just looking at it, we can speculate that probably taller parents will have taller children. And Galton's data kind of demonstrates that. What Galton was after was to fit a line to this. He was obsessed with the definition of best line. What is the best line? The best line is a line that is as close as possible to all the points on this picture. That is, even if you mingle with its slope a little bit, it's no longer going to be the closest to the entire set of points on this data set. The work that Galton did in fitting this line to this data is, from the applied perspective, is revolutionary. Nobody had done it in the context of data analysis, but there are visionary mathematicians of the 18th century, namely Gauss and Legendre, who had worked on the mathematical problem of finding the best line. They knew about Newtonian calculus and all the mathematical intricacies associated with it. So they had solved the problem of what is the best line mathematically. But it was Galton who approached this problem through analyzing data, fitting lines to actual data. Not only Galton wanted to fit lines to this data to demonstrate this sort of overall pattern, positive pattern of associations, but he was hopeful that someday, he didn't do it, Pearson didn't do it, it took a couple of decades of explorations, that one could develop some sort of a confidence band around this line, meaning that that gray area around that I've highlighted around the blue line, meaning that with some level of confidence, you can say that the association is linear and the slope is positive. So you could conclude that even if you repeated this random sampling, brought in other group of parents and children, you more or less will be within that territory of linear relationship between X and Y axes of this plot. He wanted to do further excavations of these data. He wanted to look at all the males in this group and all the females in this group. He was after fitting lines separately to fathers and sons and mothers and daughters that are in as part of his data set. And he was predominantly more interested to see whether one type of association is more pronounced than the other one. The lines here are more or less kind of look parallel. It's hard to tell that one association is stronger than the other one. For sure, the male group stands higher. So in general, we can conclude that they're taller, both parents and kids. But the problem was, where does this data come from? There's a very good statistician by the name of David Spiegelhalter, whose job is to think about statistics for public, or translating complex statistics for public. He says that what the statistics that Galton collected from the population were predominantly from well-nourished and potentially higher socioeconomic people. Think of London of 1880s, that is highly polarized in terms of socioeconomic status of its neighborhoods. Think of your famous or favorite Dickens novel, where there's a lot of the poverty around. And so, in all likelihood, people who reacted positively to his call in the newspaper and took time, could afford taking time, going to his offices and their heights being recorded, are probably part of the, at the very least, petit bourgeois category of the society. So there's a problem with the bias in the data set to begin with. But more vividly, if you look at, and you can verify that, if you look at the average height in Galton's data for male and female, it's compatible with the average height of UK citizens in 2010. So amidst 140 years of progression in terms of nutrition and so forth, you can tell that these people were selected or belong to a certain category of the society. And if you picked up a textbook that was in the subject of statistics and was published in the 60s or 70s or 80s, the data would show up, but there was probably not much of an articulation about the fact that Mr. Galton, who was Charles Darwin's cousin, was interested in the problem of eugenics. In fact, he himself coined the term eugenics in 1883. We do know now, from the lens of today's understanding of history of the 20th century, the massive amount of atrocities that were committed under the name of eugenics. And while it's hard to tell that Galton was not well-intentioned, but once you start reading through the lines of his writings, and I've done a good deal of that, you encounter places where he writes about advocating encouraging marriages by supplying able couples with incentives to have children. So this is the place to say that in 2010, in University College London, they removed the names of Pearson and Galton from all the buildings in that institution. The first part of statistical thinking, aside from all the eugenics story, the data sounds to me to be slightly, if not more, biased. So first lesson in statistical thinking. How did you generate or collect this data? Very, very important. The second lesson in statistical thinking is that most of the real world is actually nonlinear. Galton and Pearson wanted to fit lines, but the moment you get real data, you see that the patterns are kind of curved looking or curvatures. Here's a data coming from Alzheimer's Coordinating Center. It's a national center that coordinates information from different institutions and records almost every statistic that is out there about Alzheimer's disease. And one of our students, Jasmine, has plotted data for a subset of the very big data set that we have access to of the age of patients or subjects and their brain volume. Biologists in the room will tell you that it's a known fact that as you get older, your brain begins to shrink. And so it's not surprising to see some sort of a downward trend in this picture, although you can tell that it's probably is kind of bending around 70 years of age or so. So it's not straight line, just looking at the pattern, but it's somewhat curve-like. In fact, in that data set, people are either being diagnosed as having Alzheimer's disease or or being diagnosed or not being diagnosed, and thereby are categorized as having normal cognition through certain cognitive tests that they administer to patients. In fact, there are even more grained variation of those categories. Within the Alzheimer's sort of category, there's the mild cognitive impairment group in blue, and there's the dementia, severe Alzheimer's in red. And so what is miraculous is that if you look at the normal condition group, the mildly cognitive impaired group, and the dementia group, you can see kind of those patterns of brain volume, the y-axis shrinking as a function of age repeating itself. It's more pronounced, that curvature-looking thing in the normal cognition, but it's there in other places. It's definitely a declining pattern of relationships. So it probably would not be sufficient to just fit a line to this data set. In all likelihood, you want to be able to build a model that explores the nuances associated with this data. It has ups and downs, peaks and troughs, and probably are zigzaggy like this, if you wish. Okay, what is the benefit of this? The benefit of this is that if you remove all the points from this data set and just looked at that green curve, or green function, whatever it is, then you probably have a better way of exploring the relationship between age and volume of the brain at for different ages or different time points. That story applies to other groups, although you can say that you can easily see that for the dementia group, the intercept is lower, meaning that in all likelihood, if people have been diagnosed with dementia, their recording of the brain volume shows smaller numbers to begin with, regardless of age. So the very task of a statistician is to build statistical inferences about these types of relationships, which used to be a non-trivial approach or technology. If you did this stuff back in 1970s or 60s, you had to do a lot of theory in order to convince the world that these sort of gray areas around those curves are meaningful. They build a meaningful confidence spans. But nowadays, our students utilize a concept that is very cool and hip and modern called bootstrapping. And it's a byproduct of the 1980s. And they can build these types of confidence intervals around nonlinear relationships. It's a major feat in terms of technological advances and data analytics abilities of telling stories with respect to relationships between certain variables. Not only that, but nowadays our students can actually look at the contrasts between those whose brain activities were not diagnosed as having any type of cognitive impairments, normal versus dementia, normal versus mildly cognitive. And you can see that there's more zero dotted line in the contrast between these categories and the mild cognition category in contrast to full dementia. And it's very hard to tease out the differences between dementia and whether the person should not be categorized as dementia for very high, certain age beyond 90 or so, obviously, because, at that point, most brains are shrunk due to natural progression of the brain. The third lesson in statistical thinking is that there's almost always variables that you want to explore beyond what you can see. And if you want to tell a story with numbers, you have to be persistent about that. And that's what we try to convey to our students in the classroom. And it's a very, very important part of the whole concept of statistical thinking. For example, you can take this story one notch further and delve into whether the patterns, those declining patterns of brain volume had same consistency when you look at them from the different angle of whether they come from gray matter or the white matter of the brain. it might be the case that you can see in this data set, as far as white matter goes, that declining pattern is more pronounced in the gray matter. But then when you get to the cognitive impairment or dementia categories of this data set, the differences between the white matter and the gray matter become actually far more pronounced. Perhaps there's a signature in there that if you want to study cognitive impairment and dementia and aging brain deficiencies, you might want to pay some attention to the data coming from white matter. And then if you're serious about doing this, you want to probe even more. You want to delve into more aspects or more variables associated with brain. Brain comes in different regions. All these regions have definitions of certain functionalities. For example, hippocampus is known to actually be associated with Alzheimer's very vividly. Biologists and medical scientists and neuroscientists have studied that for ages. And in hippocampus, you can see that the normal condition group has significantly higher brain volume, separating itself out from the other two categories of mild cognitive impairment and severe Alzheimer's disease. Whereas it's not that easy to detect the same pattern as far as frontal lobe or occipital lobe or parietal lobe or temporal lobe or patterns or regions of the brain matter. There is an area in the brain called ethnorhinal lobe or region, which kind of is a pathway to hippocampus, and thereby, because of its connection to hippocampus, you can see the dissociation or disassociation between the green curve and the blue and red curve in a more vivid way, similar to the hippocampus area of the brain. That is, if you want to do a good, decent, thorough research in any area of science, finance, technology, and social sciences, and it deals with data, you have to be persistent, you have to keep asking hard questions and not to be satisfied. Stop, delay that publication for a while and make sure that you have a better holistic view of the story and then publish your results. It's going to be far more influential. You can delve into this data set even more. You can look at the brain volume in green or blue, is it, and pink, which is the amount of fluids, cerebrospinal fluid or spinal fluids in the brain. Again, biology, neuroscience tells us that as we get older, our brains become more, there are more fluids in our brains in contrast to younger ages. And you can vividly see the sort of backwards relationship between fluids in the brain in contrast to the volume of the brain. In fact, if you separate them out, it's as if one is the reverse mirror of the other one in a very obvious way. It is at this point that our students and researchers and data scientists can start doing some cool statistical or machine learning, as you might have heard of the term machine learning, mumbo jumbo, as I call them. And the very idea is that, for example, if you look at some data to the left, I know the true state of the diagnosis of those patients. Greens are normal cognition, blues are mildly cognitive impaired group, and red is the dementia group. And to the right is the prediction associated with those three groups using a technique called neural networks that actually up to 88% correctly figures out what these three categories are. In other words, a predictive modeling recognizes the blue as blue, the green as green, and the red as red 88% of times for a very complex, intertwined, and non-trivial data set like this. And I'm showing only a portion of the data set because it's easier to see the relationships for a smaller data set. That's a magnificent accomplishment for modern data science. It was very hard to get these numbers and this level of cognition or correction or correct classification up until the 2000s, where really is the revolution of machine learning and statistical learning. We have a very powerful, speaking of Alzheimer's, we have a very powerful Alzheimer's program on this campus, led by my esteemed colleague, Dr. Archana McElligott. She's sitting in the back. and sponsored by National Institute of Health. Myself, Archana, and our colleague, Dr. Matt Kahonko, have been working together for many years. And this particular grant we're very excited about because it provides incredible opportunities for our students to learn about aging brain, Alzheimer's and dementia. And in the summer, they go to USC, University of Southern California, and they work with some really cutting edge labs that are studying and researching Alzheimer's disease. And they come back and they share their experiences to the community. I think it's a very, very good example or representative of what we do as faculty, providing these opportunities for our students. Thank you, Archie. A little bit about me. I always wanted to do these stuff, which is like a lot of mathy things. And I'm not going to go over this, President Vergi, don't worry. But that was my dream. I wanted to sit in my office, have a pencil, a white sheet of paper, and dabble on concepts, abstracts. That was my dream. But that changed when I met my PhD advisor at Carnegie Mellon, Rob Cass. Rob is a good friend now, obviously, as any mentor will become your friend. He showed me the value of applied work. He convinced me that with applied work, you can make difference. And to do decent applied work in our field of applied math, statistics, you have to have strong theoretical background. That's a given. But you also have good intuition and ability to talk to scientists and learn their trades and be able to translate those abstract mumbo jumbo into meaningful recipes for thinking about science and solve hard science problems. So, you know, Rob, being one of the pioneers of statistics and neuroscience, said you have to go learn about neuroscience. All I knew about the brain was that it's located in our heads at the time, or I wasn't even sure about that. But anyways, Carnegie Mellon in Pittsburgh, the adjacent institution is University of Pittsburgh, which has a very strong neuroscience program. There are lots of hospitals associated with it. So I went and started sitting with undergrads in the back of the room. I started learning about neuroscience, and it was one of the hardest courses I've ever taken in my life. I could do math with my eyes closed, but neuroscience was hard. If you ask me what is a cell, I always thought a cell is an entry in a table of numbers rather than a biological living being. I had to read hard books like this, many chapters. I had to read them over and over again, pretending that I understand. I did a lot of this, but it really took me a while to appreciate the context of them. But as I engaged in a conversation with neuroscientists and I learned their trades and I learned the language, it became obvious to me that neuroscience, brain sciences in general, can be extraordinarily complex and intellectually challenging, perhaps even more so than some of the math stuff that I was doing at the time. Why? Because brains define us. Our brains are information processors. And more importantly, certain types of brain deficiencies, such as Alzheimer's disease, Parkinson's, epilepsy, and so forth, are worldwide and global problems. And so if someone can offer any solution in better understanding these extraordinarily complex phenomena, that would be of value to humanity in general. And from a sheer statistical perspective, brains are absolute big data units. I mean, you cannot beat that. I don't know if these numbers are correct. Nobody does. But even if it's within a ballpark of these numbers, the number of cells or neurons and their connections with each other, then you're talking about massive, incredibly large amounts of data. The big data machine is in our heads, my dear friends. And so from that perspective, it was the biggest challenge from the computational perspective, understanding how brain mechanisms define us and how we can make pathways to solve hard problems in neuroscience. The fourth lesson in statistical thinking, in my humble opinion, is to find what constitutes or gives rise to uncertainty in data. No data is perfect. There is no way you can look at all the cells in the brain and their behavior at any given moment. We have not developed that kind of technology. I will easily predict for you that we will not be able to do that, to look at every cell for centuries to come. So thereby, you have to take snapshots or look at different regions of the brain and try to understand them locally and make inferences about the global ensemble of those regions and how they communicate with each other. That's where uncertainty kicks in. To do that carefully, because you don't read the entire data, it's impossible, you have to have certain language for it. And that language, I would argue, is the language of probabilities. This gentleman in this picture is Andrei Kolmogorov. He's a towering figure in the mathematics of the 20th century. The reason he is very, very important is because he develops a language for probabilities. Before Kolmogorov, there's a lot of work that has been done on probability theory, but Kolmogorov actually creates a bunch of axioms. Axioms are cool things in math that you don't need to prove them. You just take them for granted. And you build a whole world of ideas and concepts based on them. Kolmogorov showed that you only need 3 of those axioms to build the whole syntax of probabilities, which is magnificent intellectually. You only need 3 rules to build a whole country. And then before him, there are a lot of path-breaking polymaths, such as Thomas Bayes or Pierre-Simon Laplace, who have done remarkable work on what people call inverse probability, the problem of inverting components of probability statements and building some really cool knowledge. All of this, if you connect the story of Kolmogorov's with what Laplace and Bayes did, I think you have a solid mathematical foundation for doing statistics. To me, like many other colleagues in my ranks, we feel that that story can be told through what we call Bayesian epistemology, which essentially is a way of putting probability values on what we are researching, on what is unknown to us, given that we have some data, given that we have collected some information, some numerical information. Through this remarkable engine called the Bayes theorem, we can connect that to the reverse relationship of digging information with the idea that there is an underlying machinery that have given rise to this information or data. That's the very premise of Bayes' theorem and Bayesian statistics. This is to say that I was sold on the concept of Bayesian statistics early on in my PhD work, and I started looking at the problem of neuroscience from a Bayesian perspective. And I'll give you one example of it, and then we're done with statistical stuff. But that example is that every cell in the brain, a neuron, has the capacity to fire. You hear neuronal firings or spikings. There's fireworks in our heads as we speak. And that spiking event can last about 1 millisecond. That's a very short period of time, about 1 millisecond. It differs from one cell to another cell. And if you, from a statistical perspective, if you just line up all those spiking activities as a function of time, you create something which neuroscientists call a spike train. It's a train of spikes or firings. It's a stochastic process from the language of probabilities, meaning that it's a random event, right? And the way people record those neuronal firings is that there are these tiny devices called microelectrodes. They insert them to the cortical area of the brain. The cortex is the sheet that is wrapped around the white matter. And they record neuronal activities. They train animals to do certain things. For example, a rat that runs around a maze. And then as the rat is doing that, these probes are in their head and they're recording spiking activities. So there's a lot of data coming out of that. One of the easiest and fastest way of visualizing neuronal data is a combination of 2 plots. The top part is called a raster plot. The lower part is a histogram that you might have seen in your stats education. Every tick mark is one of those spiking activities that last about 1 millisecond. And every row of the raster plot is a completion of one trial or one epoch of animal doing certain things. And so if you stack up all those trials, and if you bin the time into 5 or 10 milliseconds of bin widths, and if you collect all the tick marks that have happened within that bin and add them together, you can create a histogram that pretty much reflects the overall firing pattern of a cell as a function of time. When a neuroscientist find out that you're a stats person or a math person, the first question they ask you is that, can you model this histogram? Can you fit a little curvy thing to it? And our answer is yes, because you have to live. And so, yes, we can do that. But the problem is that they give you a lot of these histograms. I'm showing 30 of them. It's a very noisy data. No pattern is the same. All histograms are different looking. Some of them are even not happening. Look at the silent ones. Some of them are a lot of data and so forth. And they want you to develop a machinery of fitting curves to these histograms so that if you removed all those histograms and if you limited yourself to those curves only, you can build statistical inferences that are helpful to scientists about those curves. In other words, they want you to do stats for curves, for these orangey things. Thousands of them at the same time. If you are doing your job correctly, then you might be able to find certain cells that demonstrate really cool behaviors. For example, down below are some of those curves that I fitted to the histograms. That show certain patterns. The ones to the left are bimodal, meaning they have 2 peaks. The ones to the right have a lot of crescendo in the beginning and they kind of die down. And then they match with, for this animal, they match with what they call electroencephalograph recording of the animal's hands, movements, or digits. And this correlation is near perfect. Statistician's job is to find or hunt for these patterns. And modern statistical techniques, especially Bayesian classification techniques, allows for finding these types of patterns very, very coolly from a large group of curves that are out there. And then giving them or offering them to neuroscientists, and neuroscientists can write really cool papers about this muscle neuron mimicry. This looks easy. All you need to do is to draw a curve. But actually, it's a very hard task. There's a lot of math that goes into developing language for what the data is. I'm not going to go over this. I'm just trying to show off. But fit a probability model to these things, to write the full Bayesian model, to develop all the parameter tuning that you need to be doing, to develop language from one step at a time, sampling information from all the parameters in your model, and then building inferential models that are useful to scientists. There's a lot of detailed techniques or technology that goes into doing these things, but that's why we're doing what we're doing. Okay, enough with SAS. I have some, this is an outstanding professor talk, so I have some sweet stories to tell. First sweet story is about a young, shy lady who came to my office some years back. Her name is Valerie Pointer, and she's sitting right here. And she, I was an assistant professor. When you're an assistant professor, you're very careful not to do anything. So she came to my office and she was like, she said she wanted to be a doctor, a physician. And I said, well, that's good. You got to go to another department. And then she said, no, I took 1 or 2 math courses and math is fascinating. And I've heard about this stats thing, and I think stats is equally fascinating. I said, yes, definitely. Now you're in the right place. Why don't you take some courses with me? She did. She got the bug. She's obviously extraordinarily talented. And then she did undergraduate research with me, and she got scholarship and all that stuff. I've still saved her poster from 1950s, where where she did this remarkable work on neuroscience, those histograms, remember the curves and so forth? She did all of that. And then she went to pursue her PhD in statistics at UC Santa Cruz. And she did postdoc in the Bay Area. And we published together with her advisor, who's a good friend of mine, a PhD advisor. And then one day we had a job opening and she came and she interviewed and everybody in the committee liked her. And now, years after, she is now an associate professor, a tenured professor at Cal State Fullerton. That's her and me, and a legendary member of our department, Professor Amazon, who's in Canada now. But the reason I bring this sweet story is because every professor in our institution has tons of these stories to tell. I am positive my esteemed colleague, Dr. Jamshidian, is here. He's mentored so many young statisticians, such as Dr. James, who's sitting there nearby, Valerie. Every professor in our institution, regardless of what department they belong to, have stories of this nature to tell. I tell you one more, and there is a reason for that. There's a group of students who did work with me, again, on the brain. You can see the brain thingy in the left. And these students were incredible. The reason these students were incredible is that when they came to me, they had a dream. The gentleman to my right, Dewey, wanted to be an academic. He's now a professor in Michigan. The lady to my left is Jenny. She wanted to use her mathematical knowledge to help veterans. She pursued the area of prosthetics and orthotics as a grad school. The gentleman next to Jenny is Tony, who is one of the most talented students we've had in our group. He wanted to be a data scientist. He's now a senior data scientist. He did years of work at Amazon. He's one of the most clever students we've ever had. I think Maury agrees with me. The young lady next to Tony is Raina, who wanted to be a teacher in her community. And she ended up now as one of the most accomplished teachers in Anaheim School District. These people came to us. They wanted to accomplish certain things. And I think in Cal State Fullerton, we can make that happen. And I have data for it. I want to talk about, bringing grants. President Virgin mentioned grants. There are ways to provide opportunities for a large number of students in one scoop. One of them is the grants. Similar to the grant that we have at Archina, we have a grant that Professor James here, sitting here, Dr. Jessica James, with whom we provide a data science grant that allows us to get a large number of our students, incredibly talented students, and teach them the foundations of data science. And not only do that, but to take them to institutions such as the UC Irvine, statistics department. And with colleagues there, we bring some cutting edge research problems that they work on. They publish, they do poster presentations, they come back and they are ambassadors of data science to this campus. One of them, Aubrey, is here. Aubrey, can you say hi? So we provide these opportunities for our students. Again, these types of stories are not limited to what I do. Every professor that I know of has many stories of this nature to tell. I should brag about my department. This cannot be an outstanding professor. My department is my home. We spend 8, 10, 12 hours of the day in our home departments. And this story might have been shuffled out of importance because there are so many cool things happening here, but I want to bring your attention back to it. This year, the Department of Mathematics at Cal State Fullerton was selected by the American Mathematical Society as the department that makes a difference across the country. And that is huge, my dear friends. That's a major accomplishment. I don't know why books have not been written about this, but they should, right? Because the competition is fierce, and the peers of these types, or the judges of these types of awards are genuinely serious mathematicians. So we had enough evidence to convince them that we are a department that makes a difference. Why? Because there are members of our department who rethink how pandemics should be modeled. There are members of our department who publish in some of the most accomplished and important journals in the world, and they win awards for it. In the course of doing that, they engage their students who end up doing PhD work at UC Berkeley and other places. There are genuinely important academics in our ranks who are recognized by national institutions. There are incredible teachers in our ranks, such as Dr. Ichinozu, who's sitting right there, who are doing incredible work in terms of pedagogy and teaching mathematics. There are people in our department, an outstanding professor of this institution, who provide opportunities for a large number of young people outside this institution from the K-12 community to learn math, to practice math, and to become better in mathematics in the summer. And there is a young sort of cohort or cadre of mathematicians who are rethinking how mathematics should be taught in the classroom. And they're viewing the problem of teaching mathematics from a different new, fresh angle. Last story I want to say, and I promise this is the last one, is the story that President Virgie told. Sometime in the late 1980s, a young man who was living in a far, far away country that was ravaged by war and was under attack by bombs and so forth, found his way to the local library, immediate local library around him. And this was a quiet place. And he encountered a copy of this incredible magazine or journal called Chance. And he picked it up and he started reading it. He read it cover to cover. And they had to kick him out of the library because he was just fascinated, absorbed by this. And right before he left, he took note of the name of the editors of that journal, Bill Eddy and the late Steve Feinberg, who are some path-breaking mathematicians of the 20th century. And the message in that letter from the editors was that let's do some publications about spreading the ideas, deep ideas of mathematical statistics and data science to a larger community of readers. And quite fascinating, quite interestingly, as the president says, that young man actually survived that spectacle. If you had actually taken a picture of him in that library, you wouldn't have given a large chance of his survival or success in life, but he somehow did. And he ended up being the editor of that journal. And it was him who was writing these letters of editor to the community. This, of course, there's a 30 years gap between all of this, but it was him who was writing this editor's letter. And this is mostly for students who are listening to this conversation online or in this room, that with hard work and with passion for what you're doing, everything is possible. You need good mentorship, and we're very, very fortunate to be in an institution that provides that great mentorship to its students. And so, you know, if that person under those circumstances could do it, it is possible for you brilliant young minds to replicate what he had done and go far beyond. One last bit, in that country of his, where a tyrannical regime has stopped people from having basic human rights for 40 plus years, there is an uprising, a revolution, you might argue, against tyranny and dictatorship. Quite remarkably, people who are leading that movement are predominantly young people, students in universities or in high school. And quite amazingly, the leaders of that movement are women, which is unprecedented in the history of modern era, at least in the 20th century. If you study history of revolutions. The banner in that picture is the crying rally or the rallying cry of that movement. That in Farsi, it reads Zan Zendagi Azadi. And it translates into the slogan of this movement, which is woman, life, freedom. Thank you, my dear friends, for listening.
Thank you, Sam. Questions for Dr. Behseta?
When there's no questions, there are two possibilities.
Question in the chat?
Yes, no, actually, just a comment. Bravo, thank you, Sam. You made us incredibly proud. Somebody said that. Now, also,
Any other questions? Yes.
I just thank Sam for, especially for this last slide. It's important to point that out.
You said I couldn't ask hard questions,
Yes.
so this probably isn't hard. What's next on the calendar of Dr. Behseta for groundbreaking research?
Oh, yeah, that's a very hard question. I was hoping Dr. Walker won't show up, but he did. You know, after a while, you just get a kick out of mentoring students. And that's the best part of the job. From the research perspective, we're working on a variety of research problems. We're thinking about how we can fit models that explore these relationships more vividly and have better efficacy as far as previous models go. And the story of improving your models, as you know, Sean, in statistics is not going to end, right? Because there's no perfect model. Because the game is to try to minimize that level of uncertainty. So quite remarkably, computation has evolved, obviously, in the last 15 years or so. And computation allows us to do miraculous things that we just had to imagine theoretically in our heads back in the day that you and I were students. That is, for example, you can simulate from unbelievably complex mechanisms, simulate a lot of data, generate a lot of data from unbelievably complex mechanisms, and then study their properties. That was not possible back then. I should say that as my role as the director of the Center for Computational and Applied Mathematics, CCAM, we've been successful in bringing some very powerful computers to campus, supercomputers. And those supercomputers make that task of simulation quite possible. I have colleagues here, Dr. Pettit sitting there, who are doing very complex, very large data modeling. And what, for example, what Dr. Pettit and the other colleagues are doing these days was not possible 20 years back when we were coming to ranks of professors. It's a remarkable change of, or possibly the whole horizon of things that have been opened up. Very good question. Thank you.
Just like Joel. Zoom room wants a mic so they can hear you.
I actually do need a mic. Hey, Sam, thanks for
There you
sharing
go.
your story. Thanks for sharing your vision. I'm curious, I think you laid out a really good case for the importance of kind of statistical thinking, statistical literacy. We have our campus now. I think that everybody recognizes there's some barriers sometimes between things that are happening in one department and what could benefit others across other departments. And so I'm just wondering, just what's your vision for how things could change here that would help everybody with regards to specifically statistical literacy or thinking about data in new ways or better ways? And then what specific ideas might you have where we could get there in the next couple of years?
Well, I hope my esteemed colleagues who do statistics also help me with answering that question. The reality is that there's a lot of statistical expertise on this campus, and it's spread across the campus, right? Yes, there's the math department that hosts statisticians, but you can tell that there are a lot of scientists and experts in different arenas of sciences and beyond who have a statistical knowledge and are aware of the importance of being familiar with statistics and thereby analyzing the data carefully. Sean is one of them, for example. I think the next big step should be the creation of a data science program. I really genuinely believe in that. Other institutions are doing it and quite successfully, and we should, us being known as the leaders of what we do in our community, we should take that task very seriously. If there is a data science program, whether it's a minor or a major or a graduate program, that different groups have a representation in it. For example, there are active stats programs in College of Health. There's active stats programs in College of Business. There's active stats programs in sciences, obviously. If people gather about and define the commonalities, and there is a lot of that, then I think the real practical solution to this problem is to start a powerful data science program. We surely have the expertise and knowledge. We need to get together and define that as soon as we can. Others have done so, and very many other institutions are currently thinking about it. I think it's the time to start an official data science program at Cal State Fullerton. You guys
There's another
agree?
in the chat.
One question from the chat is about your study on Alzheimer's disease. Is your current research involved on possible treatments like new meds? Is there big data on current treatments?
I'm not qualified to answer that question because I don't know about there's always the biggest development in Alzheimer's is biomarkers and genetics, obviously. And that's the route to pharmacology of it, the development of drugs and treatments. But I know from communicating with neuroscientists that the language of cell biology and genetics associated with cells is so much improved these days that they can actually pinpoint from a genetics perspective what gives rise to these types of problems and diseases. So it's hard to tell there's big data there because when you get into cell biology, it's the study of units unto themselves. There's a lot of chemistry and physics and biology involved with that. So it's at the unit. But the data piece of it is that there are very many institutions who simultaneously are doing this type of research. Whether that translates into drugs or not, that's a hard story. Whether we will find a drug that cures Alzheimer's or whatnot, I would argue that there's still a long way ahead of us.
Really good talk, Sam.
Thank you.
So I guess I was wondering your perspective based on like high performance computing that you alluded to earlier, right? So you mentioned that 20 years ago, we didn't have the technology we have now. And when I think of that in my field in physical chemistry, right? So when my PhD advisor was going through her journey, we didn't have the same technology, but what they did have was the ability to come up with clever models that simplified the physics and gave deep physical insights. And so I guess I think maybe can comment on the tension between like that way of thinking, developing simple models that give insights versus the big guns of, you know, blasting with huge data sets. Well, maybe some of the insights could be lost.
Oh, that's such a clever and important question. I appreciate that, Andrew. The way many of us are doing statistics is that we try the best as we can to simplify the story. If you give me a multi-dimensional or multivariate problem, I start with looking at every single one of those variables one at a time. And then a good deal of statistical research is just probing and being curious about how these relationships possibly can be related to each other. And that's ultimate simplicity. There's no modeling, there's no math, there's no alpha, beta, gamma yet at that level of thinking about problems. Someone argued that applied math is significantly harder than pure mathematics. I don't know about hard or easy, but it takes a lot of guts and tears, sweat, and blood in order to do applied mathematics, because you can develop all these fancy models that have very good constructs mathematically, but in action, they may not respond to the scientific environment in which data is justified. So my immediate reaction to that is that if a statistician wants to be useful to sciences, first they have to develop some sort of a dialogue with the scientist, understanding their language and their problems. And then definitely the solution is to start simple and then build around it. Almost every work that we are doing begins with intuition. Intuition has no math in it, right? It's just some abstract relations in our head. We go to the lab and we run some show and hopefully it will work. And then we say, okay, now let's write the math. Or simulate or run machine learning and all sorts of mumbo jumbo. So to me, you're absolutely right. It's an inductive body of knowledge, meaning that looking at little pieces and then trying to put those pieces together to solve the puzzle. Absolutely. That will never go away. That's part of scientific method. Yeah, right. Regardless of how sophisticated our math can get or modeling can get, that point of view about solving hard science problems, inductive approach, in my view, is there rightfully to stay? That's a very good question or point. Thank you for that.
So first of all, I want to say that, your talk was fascinating. I just got really excited about this slide that you're showing, and that's why I only commented on that. So let me just.
For those who don't know, Maury and I come from the same place. So we have huge emotions, a large amount of emotions invested in what is happening in Iran right now. You cannot help yourself turning the TV on and looking at what's happening. It's immense amount of emotions that, because we've been away from Iran for decades, ever since I came to US, I've never been back. I don't want to be back to a country that is run by thugs, basically. So it's very emotional for us. Anyways,
So
sorry.
anyway, but now I want to go back to some more serious stuff. Well, this is very serious, but I'm just talking about CSUF serious stuff.
Yes,
And the idea that has come up about data science program.
right.
So maybe you can share your thoughts about where we can start on this campus. Where does the conversation has to start? I think this is very important, as you said, and maybe this is a good place to talk about. Let's get this started.
It's definitely a very good place because we have the president of the institution sitting. I mean, we couldn't have asked for better. And the high-ranking members of the community, the deans and chairs. So absolutely, we are good at forming committees. I've been involved with 200 committees. So why don't we do that? Why don't we take this opportunity to call upon anyone who's interested in the creation of a data science program? If you're listening to me right now online, in person, if you're going to watch this show later after it's recorded, I, as a humble member of this community, are calling upon a group of people to gather about and work on defining a program in data science. Again, the stakes are high and a large group of people are interested in this, right? It's not limited to one or two colleges. I think there's a large group and there's so much overlapping interest that I'm sure that we can as a community define that. So I think it's, I don't know how you define such wide angle, wide ranging committees, but people, I'll buy the coffee for sure. If you're willing to. My office is in McCarthy Hall 157. Yeah, so I think now that we have President Virgie amongst us, we can definitely make this happen. Let's start talking about the creation of data science programs.
All right, so this is Valerie Pointer. So I was his student, now colleague. So I think a important part of that story that I would like to mention right now, especially at this institution, we have a lot of first gen students, and I'm actually a first gen student. And I have to say, all I knew going into college, like I thought you could be a doctor, a dentist, a lawyer, like just what you see on TV, right? And so I decided to go for doctor. It's a good thing that that I stumbled upon Sam, or vice versa, or chance had its hand at it, because I was one of the ones that had to use the eye wash station in the chemistry class. So when I started taking math classes to up my GPA so I could, actually become a medical doctor. I knew this was the universe telling me something. So, but talk about people who do randomly come into your life and literally change your entire trajectory. So, Sam, you were that person for me. And going back to that idea of chance, I mean, your life story is incredible, and lots of happenstance and chance is part of it. However, there's a book called Outliers by Malcolm Gladwell, and there's another element to becoming a great person other than chance, and that is that you also have to have the greatness within you to go with that chance. So.
Such a lovely sentiment. I wonder if are there any other burning questions? Okay, well, Sam, thank you so much. It was
Thank you very
wonderful.
much.